This problem is an application of optimization of multivariable functions. It says design a rectangular milk carton of width W, length L, and height H, which holds 542 cubic centimeters of milk. The sides cost 2 cents per square centimeter, but the top and bottom cost 4 cents per square centimeter. Find the dimensions that will minimize the cost of the materials involved. So the first thing I'll do is I'll just write down my variables. We've got W will stand for the width. L stands for the length. And H can be the height. I'll also draw a little picture of the situation, because that can often help us understand what's happening. It's a rectangular box, and we also want to write down any formulas that might be useful here from geometry. So the volume of a box formula comes to mind. Volume equals length times width times height. That formula ends up being part of the constraint equation. A constraint equation is a requirement in the problem here, and here they're saying that the volume has to be 542 cubic centimeters. We also want to find what is called an objective function. The objective function is the function that we're trying to minimize or maximize. And they said minimize the total cost. So we need a formula for the total cost. Now, the cost is going to depend on the surfaces involved and their dimensions. So right now I'm going to make it a function of 3 variables, length, width, and height. I'll multiply the rate of cost times the area. Now they say that the sides are 2 cents per square centimeter, so I'll multiply 0.02 times the sides. But what are the sides? Well, we've got a piece in the front, which is W times H, and there will be an equal surface, equal in magnitude, but on the other side. Here we'll have L times H, and on the opposite side of that we'll have L times H as well. So we're actually going to have 2WH plus 2LH. That'll take care of the sides. Now we need 0.04 times the top and bottom. The top here has dimensions LW, and the bottom will have equal dimensions of LW. So let's put those in. Okay, so far so good. But we do want to get this equation down to 2 variables so that we can use our techniques of minimization and maximization. So what I'm going to do first is I'm going to rearrange the equation here, LWH equals 542. I'm going to solve it for one of the variables. I'll get L equals 542 over WH. Since that's a requirement, I can now take that and plug it in wherever we see L in our objective function. This will allow me to eliminate the L variable and get it to 2 variables, which is what we need. Alright, so we're going to have 0.04 WH plus 0.04 times 542 over WH times H plus 0.08 times 542 over WH times W. Okay. We'll cancel what we can. Great. At this point, we're ready to take the partial derivatives. So we'll need partial derivative of the cost with respect to W, which will be 0.04H minus 21.68 over W squared. I'll find the partial with respect to H, 0.04 W minus 43.36 over H squared. And now, just like before, we want to set each of these partial derivatives equal to 0, and then we'll try to solve the system simultaneously for the answers. Okay, let's set them equal to 0. And I'm going to use an algebra technique here of getting one variable alone in an equation, and then I want to get that same variable alone in the other equation. The reason why is we can now take the results and set them equal to each other. So we'll get 542 over W squared equals the square root of 1084 over W. And now we'll just solve for W. I get that the width is 6.47 centimeters. I can now go back to another equation from the past that we had here. H equals 542 over W squared. That's 12.94. And then we want to find the length. There was a formula from the past, 542 over W times H. And the length is 6.47 centimeters as well. All right, that gives us the ideal dimensions of this milk carton, which would minimize the cost of the materials.